We are at Heaps. I'm starting out with the bra on the screen. I just recorded like 6 minutes of this video only to see that I wasn't shown. Not that you need to see my silly looking face, but here we are for go number two. How do we feel about a new data structure? I say bring it because this one is fun. It's going to be easy. We're more mature. We're ready to actually knock these out. So, what is a heap? A heap is an abstract data type, similar to stacks, queues, trees. These are abstract data types. We say that they're not built in the core feature set of Java, but were added on afterwards. We need to define their behaviors and dictate whether or not a given data structure is a heap. So, what is a heap? More specifically, what does a heap do and how does it work? It looks like a tree. In fact, we're going to explain it's a complete tree. But a heap has a specific property that each node must follow in order to make that tree become a heap. In a heap, all values stored in the subtree of a given node must be less than or equal to the value stored in that node. And this is true for what is called a max heap. We have two types of heaps. We have a max heap, we have a min heap. They work the same. The difference is simply which value gets stored at the root. Do you want the maximum value to be stored at the root? Or do you want the minimum value to be stored at the root? It's your choice. You might wonder why. We're going to get to that. But that's the difference. We have a max heap and a min heap. This rule that I just read is for a max heap. So one more time, all values stored in the subtree of a given node must be less than or equal to the value stored in that node. So if we simply look here at the root, all values on the left side of the root are clearly smaller than the root. All values on the right side of the root are clearly also smaller. There is no relationship whatsoever between nodes on a same level, or no relationship between these nodes and these nodes. None of that bigger to the right, smaller to the left of a binary search tree. The only rule that we've heard thus far is for a max heap, which this is, all nodes that are in a subtree of a given node must be smaller than that node. And that's not only true for the root, it's true for every node. So you look at 19, all the nodes in the left and right subtrees of 19 are smaller than 19. Look at 36, all of the nodes that are children and their children of 36 are also smaller than 36. This is known as the heap property, and it is in fact what makes a heap a heap. It is this property. So if B is a child node of A, then the value of node A must be greater than or equal to the value of node B. That is a max heap, where as a result of this rule, the root will have the largest value. As mentioned, we can also have a min heap. Same concept, but now the rule is flipped, where for each node, all of the children within the subtrees of that node, those children must have values that are greater than that node. And that's true for the root and every node. So look at this root node of this min heap. This root should have the smallest value, and all the nodes on the left will be larger, and also all the nodes on the right will be larger. But that's true for every node. Pick 2. All the nodes to the left of 2 and to the right of 2 will be larger than 2. That's a heap. But what is a binary heap? A binary heap has one other property it must adhere to called the shape property. And this effectively says that the given tree, it must be complete. We are experts at what complete means. Every level of that tree must be completely filled, level by level, with only one possible exception, that lowest, that bottommost, lowest, last level. It doesn't have to be filled, but if it's not filled, all of the nodes on that level must be aligned to the left side. So we understand a heap has this invariant, this rule that we just described for a min heap and a max heap, and it also has that shape property. How do we build a heap? This is just going to be a bird's eye view. We're going to build a heap in more detail, but really we want to start with just building a complete tree. How does that work? It's really level by level. We start with the root, and then after adding the root, you add the left and the right child of the root. Then you add the next level, and then you add the next level, and so on. Now, in a heap, every node, of course, will have data members. It's obvious, right? But also, one of those data members, usually in particular, will be a key value that is used to determine that ordering in the heap. Are you smaller than me? Are you greater than me? Where should I go? Should I be your parent? Should you be my parent? And we're going to use that key value to compare the values of the nodes. Of course, we can see here, this is a max heap. Pick 23, all the nodes that are children of 23 are smaller. Pick 35, all the nodes that are children of 35 are smaller. Even 27, all the children of 27 are smaller. And the maximum value is found where? At the root. New nodes are always added at the lowest level, the very last level, and they're inserted from left to right. Important to mention again, there is no relationship between the data items of a given level. Even if the nodes have the same parent, there's no relationship between the siblings. You can't say the left will be smaller or the right will be larger. There's no relationship among those siblings. The only ordering property of a heap is the one already defined, where it's either going to be a max heap or it's going to be a min heap. What's the value of this heap? Well, first of all, the tree never becomes unbalanced. That's really the value of just adhering to that complete tree property. A heap is not a sorted structure. It's not sorted. A binary search tree can be sorted, certainly, right? A heap is not a sorted structure, but we say, in fact, it's semi-sorted because of the fact that the greatest element will always be at the root if it's a max heap, or the smallest element will always be at the root if it's a min heap. And there's a value to that, which we're going to come to. So we really say it's partially ordered. A given set of data can form many different heaps based off of the insertion, based off of the order by which those nodes are added to or inserted to the heap. So I say here, okay, great. Whoop-de-doo. What is the value? We know what a heap is. We know what a binary heap is. How does it help us? What is its purpose? That's really the question. Binary heaps are used to implement another data structure. They have one purpose in life: to actually implement another data structure, a very straightforward data structure that all of us have heard of. So we maybe haven't heard of a heap or a binary heap, but there's another data structure that we have heard of that you can implement in many different ways. But it turns out the best way to implement this data structure is using a binary heap. And what data structure are we referring to? A priority queue. Now, you may not have heard, I said you've heard priority queue, but you can make sense of it. We know what a queue is. A queue is a waiting line. What is a priority queue? Well, we're going to cover that. A priority queue is exactly what it sounds like. It's a queue. We have a line, but the first person in that line is not necessarily going to be the first person that will exit that line. Rather, the queuing order is based on a priority. So if one person comes into that line with a higher priority, that person goes immediately to the front. And the comical thing is, I like to often ask, so think of what might be a famous priority queue. And traditionally, in every textbook, and frankly, even when you ask this question at universities and colleges around the United States, even around the world, you'll almost always get the same answer, as you should. But here in Florida, which is where I'm based at the moment, don't get that answer. Instead, when people say, well, where is a line when you're in it? And then these punks, they go in front of you. Oh, that sounds like Disney World and Fast Pass when they used to have that, right? So jumping the line, which is just comical. But in fact, the most famous example that's in every textbook and students normally think about, an emergency room. You might be the first person in that line with a cut on your finger you need 2 stitches on. Someone comes in, heart pains, chest pains, something else going on, slurred speech, they're going to go to the front of that line. This is a priority queue. Requests are inserted in the order of their arrival, and the request with the highest priority is going to be processed first. It will be removed from that queue. How do you indicate priority? You're the programmer, you decide. Usually it would be some number. Does the higher number mean a greater priority? Does the lower number mean greater priority? that is up to you. You are the developer. You make that choice. It might make sense in your mind that smaller numbers are more prior, have a higher priority, or greater numbers. It doesn't matter for our purposes. You simply choose why we have both a min heap and a max heap. Because ultimately, a heap is how we're going to implement this priority queue. But before we talk about using a heap to implement a priority queue, we understand what a priority queue is. What if we don't know what a heap is and I say, okay, let's go implement a priority queue right now. Let's actually just try to think about how we may implement a priority queue. And you might be a bit confused. Well, what do you mean? Well, exactly what I said. We want to implement a priority queue. How would you do it? In the same way that we introduced a stack and we understood what a stack is. And I said, okay, well, now ultimately you need to build it in Java in your given language. How would you build a stack? How would you build a queue? What did we ultimately use? We implemented the functionality of a stack using both arrays and linked lists. But we restricted the behavior of that array and of that linked list to make it perform and behave like a stack with only access to the stack via the top, via the push and the pop. So in that same way, how would we actually implement a priority queue? So we can use a sorted linked list where higher priority items are always added at the front of the list. We have this checkout line in a supermarket. People who are more important maybe can cut the line. That's pretty gangster. What would be the running time of this sorted linked list if we're implementing a priority queue, but we're doing a sorted linked list? So anytime someone comes into that linked list and they have a higher priority, they need to go at the front of that linked list so they can be immediately DQ'd. Well, therefore, the insertion is going to be O of n, right? Because when we're trying to insert a new person into that linked list, you have to find out where they should be inserted based off of their position, and that will be an O of n search to determine that. We're going to keep it in sorted order. It would be an O of n search to find that insertion location. So the insertion is slow, O of n, but now deletion, super fast. Why? It's O of 1 because we know that highest priority item is at the front. That was with the sorted linked list. What if I say implement a priority queue using an unsorted linked list? How would you now make that happen? And we're confused. Well, if it's unsorted, that means what? We can insert anywhere into this linked list. We just add it, therefore, at the end, O of 1. There's no need to look for position. It's unsorted. We add it at the end with O of 1, but now when we want to remove that element with the highest priority, we have to search over this entire linked list, which is an O of n search. So insertion's O of 1, but now deletion to find that highest priority item would be O of n. I don't have this on the slide, but think about one more example of what about using an array? If you say, I would like to use a sorted array to implement a priority queue. Well, you need to now insert into that array. Now you can find your insertion location if it's sorted using binary search. There's a smart way you can do binary search to find the spot where you need to insert. So that would be a login to find it. But ultimately, when you insert into that array, shifting. So big O, what if the spot you find to insert is at the beginning of the array? We now have to shift everything over, which is O of n. And now when we want to remove that item, we can find it in log n, but now we have to shift back, which is O of n. So really the bottleneck of an array-based implementation is going to be O of n super slow. So ultimately, how do we implement a priority queue? The answer is using a binary heap. So what's really cool here is that the objective is we want to implement a priority queue. How do we do so? We ultimately use another data structure, a heap. So one abstract data type to implement another abstract data type. Ultimately, the running time for both insertion and deletion into a priority queue that's implemented via a binary heap is O of log n, For insertion, an O of log n. For deletion, remember I said that when we come back to it later and I say, analyze the running time. Well, you're going to be like, well, you told us it was log n earlier, so I'm assuming log n. Let's understand why when we break it down. But finding the minimum value in a min heap or the maximum value in the max heap is just O of 1 because we said that minimum value will always be at the root if you've chosen your smaller numbers to have the highest priority. Or if you chose a different scenario, max heap, where the greatest numbers have the highest priority, well, that maximum value is always at the root, so you can find that person in O of 1. Now, when we remove that person from the root, we need to fix the heap. There's a cost involved. That cost is log n. So ultimately, insertion and deletion end up being log n. Let's look at how we now maintain this heap, this priority queue structure. But first, we have double the fun on this incredible bike fail here. I don't get enough of these pictures, my apologies, but these are just so incredibly awesome. We had two of them back to back on these posts. This is back when I was teaching at another institution. I've said it. I don't want to say it again because I don't disparage it. It's my alma mater. I love it. But man, how are you locking your bike to that? And how do we have two of them locked to that post is incredible. For the love of commenting, when your colleague asks you if you're going to go back and properly document your code and you say, I don't think, joke about that. But commenting is super important in industry. You're not going to be doing inline comments, but you might type 3-4 lines of code to fix something, and you're going to be putting maybe 2 paragraphs in an offside commenting system related, a tangential commenting system that will then be working with that. That made no sense the way I said that, but that's okay. No editing on this video. You're going to have your comments that you're going to be putting not in the code, but in another program that will go along with that code. You can like click on it and see, hey, what did they do here? Comments are super, super important, and we want to develop good habits now. Adding nodes to a binary heap, how does that work? Let's assume that we already have the existence of a current heap. The heap has to follow this shape property. The tree must be balanced. Insertions will always occur at the next available spot, at that next level of the heap, going from left to right. Think about what happens when you insert at that next available position. And it may not hit you immediately, but think about if we have a heap with maybe 100 nodes and it's a max heap, the maximum value is at the root, then the next level have the next largest, the next level have the next largest, and so on, 100 nodes. When you randomly add a new node, or let's word it that differently, when you add a node and that node has a random value, at the lowest level, going from left to right, you add this new node with a random value. What statistically is most likely to have happened when you add that new node at that lowest level? That heap property is no longer going to be maintained. Consider if you have this max heap, we have what, 3, 4, 5, 6, 7, 8 nodes. We would add a 9th node, and it's going to be some random number. What's the chance that this 9th node we add is going to be smaller than 27? It's a good chance, but there's also a good chance it will be greater than 27. And when we add this new node, such as 42 here, it's no longer a heap. So adding that node can happen in O of 1 time. You might be wondering how do we save this tree? We'll get to that later. But trust me that adding this node at that spot is O of 1. But the problem is we no longer have a heap. Why do we not have a heap? Because the rule says on this max heap that every node, the rule must be true where all of its children and their children and so on must be smaller. Well, if you look here, that's not true. 42 is bigger than 27. Frankly, it's bigger than 35. We no longer have a heap when we added this new node at that last position. What do? We have to fix it. It's called percolate up or percolation upwards. In order to fix this out of place node, we simply follow the following procedure. If the parent of the newly inserted node is smaller than this new node, we simply swap them. And we swap them again and again and again as long as that if statement is true. And this is, of course, valid for a max heap. If the parent's smaller, we have to swap it because it's out of place. It would only be out of place there on a max heap. This counts as one percolate up step of doing one swap. Another swap would be another percolate upwards step. And we simply continue this process until the new node finds its correct position. So let's go look at it here. Clearly, when we look at 27 and 42, they're out of place. We simply swap them. Are we done? No, you can see we're not done. 42 and 35 need to swap. Finally, you see we are done on this example. No more swapping is necessary. 42 reached its correct location. We now have a heap. This process is called percolate up. Other textbooks call it heapification upwards. You get the idea. Insert at the next available spot and then percolate up as needed. We want to understand how it works, but we also want to know what is the running time. So think about this. I want to come back and look at that again. We insert here, that's O of 1 to actually place it. But now what's the running time to fix it? Well, think about it. We swapped again, and maybe you swap again all the way up to where? When would you stop swapping worst scenario? You'd stop swapping worst scenario when you get to the root. The running time of making that happen. The insertion we mentioned is O of 1, but now fixing it, what is the cost of fixing it? The answer is O of log n, or you could say O of the height of the tree. But because this tree is perfectly balanced, we have a guarantee that its height is log n. We've mentioned that if we have a tree of 1,000,000,000 nodes and that tree is perfectly balanced, the height of that tree is only a 30. And some people, if you're hearing that for the first time, you're like, wait, what? And you want to go draw out a tree, get your calculator. If you draw a tree, a binary tree with only 30 levels, that lowest level will have 1,000,000,000 nodes, and I promise you, you will not draw out that entire tree. So here, because that tree is complete, so it's a balanced tree, the height is guaranteed to be log n. So the percolate up, worst case scenario, we need to go up the entire height of the tree, and that height is going to be log n. Super cool. So the insertion ultimately is log n because it's O of 1 to place it, and then it's O of n to actually fix it. What about now deleting nodes from a binary heap? We want to write this method called delete min or delete max if it's a max heap. Which node will we always be deleting? This is not meant to be challenging. You're like, wait, oh yeah, it's going to be a max heap. So I'm going to always delete the maximum node from that heap, which is where? It's the root. So the whole purpose of using a heap to implement a priority queue is because that highest priority value is always at the root. Whether you use a min heap or a max heap, that's because you as a developer, you might want the smaller number to be the highest priority or the greatest number to be the highest priority. Your choice. You have both options with a min heap or a max heap. But the purpose of using a heap is now this highest priority item will always be at the root. So in a priority queue, we would always need to delete that first element, the one with the highest priority. We will always be deleting the root of this tree. And that's super easy to actually have access to the root, what a tree is. So we're going to simply delete that root. But what happens when we delete the root of a tree? We have a tree with no root. So clearly it's not a heap anymore. We have a tree with no root at all. We need to fix that. Let's get a visual and understand what actually happens. What we're going to do is copy the last node of the tree into the position of the root. We're then going to remove that last node so we don't have duplicates. But of course, think about when we move that lowest node into the position of the root. Clearly, it's going to be out of place. So now we need to do what? You can guess the idea. Percolate down or heapification downwards. We're going to swap this new root node with the greater of its children That is if it were a min heap here, not a max heap. That's a percolate down step. Let's look at a visual. So here we have this heap. We would like to delete 45. 45 is leaving the priority queue. It's going into to ride whatever new ride, it's going to go ride Space Mountain. That's old school. It's going to go ride another Thunder Mountain. Give me another one. The Disney, the oh my gosh. Sleeping Beauty. That's not even the best one, but it's a good one. You're dequeuing. 45 is going to ride Sleeping Beauty, but now we need to fix a heap. What do? Well, we just said we're going to remove 45. It's gone. And now we effectively move 27 up to the position of 45. Now, what really happens is we're really going to take the contents of 27, save them over temporarily, delete 27, and then simply put those values back into the position of 25. But as a visual, what really happens? We're going to remove 45, and we're going to put 27 at 45's place. How that happens in code, we'll get to later. But that's really what's going on. Simply delete 45 and do what? Put 27 in its place. Well, when you do that, it's almost guaranteed to be no longer a heap. Because this was a max heap, we can see that 27 is clearly not greater than its two children. So what do? We have to percolate down. What is the process? Swap 27 with the larger of its two children. I paused there for emphasis. Swap 27 with the larger of its two children. So we're going to swap 27 with 42. That's one swap. We're going to swap 27 with 35. That's another swap. And we keep doing this as long as the parent node is smaller than one of its children. Or than both of its children, no, than one of its children. We're gonna swap it with the larger of its two children as long as it has a child that is greater than it. So we swapped once, we swapped a second time, and now we see that 27 is finally greater than both of its children. And again, this rule here is for a max heap, and that is the idea of percolate downwards. So 27 reached this correct spot, and we percolated down twice. Once again, what is the running time to delete from a heap? Well, the deletion itself, since we have access to that root node, it's O of 1. It's pretty easy, okay? But now we need to fix that tree. So we need to basically move that 27 to the root, which is what we did. That happens in O of 1 time. So just trust me there and we'll see how that works. But now the percolation downwards, it is log n. Because worst case scenario, what's going to happen? This new node we put at the position of the root, it will need to percolate, worst scenario, down what? Down the height of the tree. So the height of the tree is log n because it's a perfectly balanced tree. It's a complete tree. So worst scenario is we need to percolate down the height of the tree. And the running time, therefore, is O of log n for deletion. And guess what? One more page. Let's go. Just to plant a seed here. We're wanting to implement a priority queue, right? And to do so, we use a heap to implement that priority queue. But how do we actually implement a heap? You might be thinking, didn't we just discuss that? Didn't we talk about inserting into a heap, deleting from a heap? Well, we have visualized this heap as a tree because it really is a tree. That percolation upwards and downwards, or heapification upwards and downwards, it therefore makes sense in theory. But how do we implement it in code? Or can we implement it in code? Turns out there is something super cool and super unique of how we ultimately implement that heap, but that is for the next video. Wasn't that? Maybe it was. A demotivator from despair.com, one of my favorites. I think we've seen it before, but a worthwhile revisit. Procrastination, hard work pays off over time, which it does. But laziness, big brain, laziness pays off right now. You know it does. It has been fun. Take care. Please leave a question, comment if you need anything.